Good afternoon. Today we'll start a new chapter and we will be talking about position sensors. Since this topic is quite broad, we'll be talking about it also next week. Next week, next class. I want to remind you that next week is Easter Monday and therefore we do not have any classes. So our next lecture will be in 2 weeks on April 9, and this includes also the lab classes. So if you look in the schedule about the classes scheduled for next week will not happen, and we will follow the list and we will be doing the next one in the list. So there are no classes next week on Monday. It's free day. So we'll meet on April 9, lecture and lab class. Today we'll be talking about position sensors. Position sensors are very important because they will include sensors for linear displacement, for angular displacement, but position sensors can also be used to detect objects that you have on conveyor belts. They may be used to detect position of axes on some manufacturing machines and so on. So today we'll cover just some selection of the sensors for position, and we will finish the remaining sensors next week. There are many types of position sensors. You may distinguish them based on various criteria. One of the criteria that you can have is if the sensor is measuring linear or angular displacement. So, for example, here I have a sensor for linear displacement, so you may use it to detect some position of a linear axis. But some other sensors may be designed for angular displacement, such as a sensor like this. So then you obviously may transfer between angular and linear displacement if you use a gear, for example. But in many cases, it is more convenient to use a sensor that directly gives you what you want, so linear or angular displacement. As you will see, some sensors are basically designed for one, or they can be used for two. So they can be used for linear or angular, or both if you design the sensor in other way. We'll also see that typically the sensors for linear displacement, they may have some trouble with thermal expansion. So then it would be better to take the sensor for angular displacement. The second criteria for the sensor is if the sensor is absolute or relative. Here it means what is the behavior of the sensor after you turn it on. If it's an absolute sensor, it will give you directly the correct information. For example, well, all the sensors I have here with me today are absolute sensors. So let's say I turn the machine off in some position, then it moves somehow, and I turn it on in this position. And when I read the signal from the sensor, I will directly see that this is the position and I will have the correct data. So this is the absolute sensor. A relative sensor, on the other hand, means that you turn it on at an arbitrary position, and you need to first move to some reference position, and you count from this reference position. So a relative sensor needs the movement to the reference position. It's a major difference because some applications will require that you use an absolute sensor. For example, absolute sensors are used to control electric motors. They control speed and torque in trains, in trams, for example. And the sensor that is mounted in the electric motor measures the absolute position of the shaft of the rotor. So if after I turn it on, I need to read directly the position because the current in the motor should be controlled by the current position. and there is no way I can move the motor forward and backward in this application. I need the position right from the start. On the other hand, there are many applications where you don't need this behavior. For example, CNC mills. You turn the machine on and you can go to an end stop and say, from this end stop, this will be position 0, and I can count some pulses. The advantage of rotative sensor typically is that they have a more finer resolution. Let's say roughly 10 times larger resolution than absolute sensors. So if your application requires the absolute position, then you will have lower resolution. But for applications like electric machine control, that's not an issue. But if you need a really fine resolution, you will definitely need to go for a rotative sensor. The third criteria for position sensors may be what is the principle of the sensor, if it's an analog sensor or if it's a digital sensor. The sensors that we will be discussing today are all analog sensors. So they are able, in theory, to give you an infinite resolution. The sensor itself is not limited in resolution, so you can measure with an infinite step what is the position. But then obviously the limitation will be the electronic circuit. How am I able to read the signal? It will be most likely read on some computer or on some digital voltmeter. So then this will be the limiting factor with accuracy. But the sensor itself, if it's analog, does not have this limitation. A digital sensor, on the other hand, has this limitation right from the start. So the principle of the digital sensor is such that it has some finite resolution. It can be very small, but in any case, there is this finite resolution. The fourth criteria may be if the sensor is continuous or if it's a proximity sensor. A continuous sensor looks like this, and it is able to give you a signal that is proportional to the current position of your object. On the other hand, proximity sensors, they just say you object is there or object is not there. So proximity sensors detect if you see the object or if you don't see the object, but they do not give you the information about the distance between the sensor and between the object. Continuous sensors are typically more expensive, so they are not good in applications where you need like hundreds of those sensors. And proximity sensors are typically used in manufacturing lines, for example. If you want to detect an object, if you want to detect a product on the manufacturing line, you just need to see if the object is there and if I can pack it, for example, in a box. I don't need to measure how far the object is from the sensor. So proximity sensors are only detecting the presence of the object, and the signal is only 1 or 0. Signal is there, signal is not there. Proximity sensors are typically less expensive than continuous sensors, and we'll also see some examples of applications. The sensors I will show you will use the fact that electrical resistance can be somehow transferred, well, position can be transferred to changes of electrical resistance, capacity or inductance. Today we will discuss only resistance and inductance, so only those two, and the other principles we will be discussing next week. Let's start with resistive sensors. A resistive sensor is a very simple device. It is in fact just a variable resistor. So for example, here you have a variable resistor. This one allows you to measure angular motion, and it's basically nothing else than a resistive track where you have two fixed terminals and one slider, one variable terminal, and you measure how is the electrical resistance of this connection changing with the position. So we have this schematic. This is the sensor itself. This terminal and this terminal is fixed, and this is the slider, and I can move the slider up and down. The initial resistance of the sensor, I will call it R0, is typically a few kilo ohms, and this will have also an important effect on the behavior of the sensor. We need a power supply, so it's powered with a DC voltage, since I'm measuring the changes of electrical resistance. And the slider that you see here divides the resistor R0 into two sections. One R2 is here and one R1 is on the top. There will be also a relation between R0 and R1 and R2, obviously. So R1 plus R2 equals R0. We do not measure directly the electrical resistance, although we could do that. But we measure the output voltage of this connection. So here there will be some voltmeter. I will represent the properties of the voltmeter by this resistance, RL. I will call that load, and we will see that unfortunately it will have a large effect on the steady state characteristic and on the properties of the connection. This connection is called a voltage divider. So you have some input voltage, and the output voltage will be a function of the input voltage, but also of R1 and R2. In other words, also it's a function of position. That's what we want. Now, if we analyze the voltage divider connection, we may derive those equations. So here, the output voltage, V2, equals to V, the power supply voltage, times this resistance. This resistance is R2 in parallel to RL. That's what you see here. That's the equation for two parallel resistors. And then here you have this resistance plus this resistance. So it's R2 in parallel to RL plus R1. If you simplify this equation, you will get this. But here we see that the output voltage depends on the input voltage. So if this voltage will change, there will be also a change in the output voltage without a change in the position. So this means that the input voltage needs to be stable, controlled to some level. From this equation, we can also see that the output voltage depends also on the resistance RL. In other words, it will depend on what voltmeter do we use. If I use a different voltmeter with a different resistance, I will have a different voltage, although the sensor and everything else is the same. And here, R2 and R1 are the function of X, so there will be a dependence on position, but it will be a nonlinear dependence. Now let's simplify a little bit more this equation. We know that there is a relation between R0 and R1 and R2. So I will use some other formulas to simplify this. So let's define that the slider is moving from the bottom part to the top part, and that if it's all the way down, it will be in position 0, and if it's all the way up, it will be in position 1. So this will allow us to compare other sensors. We will eliminate the dependence on the resistance and on the position, and we will be able to plot all the sensors in a single chart. So here you see that R2 equals X times R0. So if X is all the way down, I have here R2, and if it's all the way down, X is 0, so R2 is 0, and R1 equals to R0. So those equations will allow us to eliminate the R1 and R2 from the formula. And we will also define a ratio between the resistance of the load and between the initial resistance of the sensor. So here I have the resistance of the voltmeter, and here R0 is the resistance of the sensor itself. Let's say R0 in the sensor I have here is 5 kilo ohms, and if I have a voltmeter with 5 kilo ohms as well, it would be equal to 1. This will allow us to plot the steady state characteristic of the sensor. Now, if you substitute all this into the previous formula, you will get something that's really complicated. And I just want to show here the result. The result is that the output voltage is still a function of the input voltage. It is a function of position, x, but it's a nonlinear dependence, and it's also a function of the load resistance. So in general, you see there is a nonlinear dependence. But if you use a suitable voltmeter, you may get very close to the linear dependence. This equation, this formula, we want to have it a linear equation. So the only way how I can get it to be linear, or more or less linear, is if I would be able to eliminate this influence of the k. So it means that if you make the value of k very large, then you will get a linear equation. If you calculate a limit of this formula when k is going to infinity, you will get this. Now, what does it mean? It means that I need k infinity. And this means that I need a very high input resistance of the voltmeter. In other words, if the voltmeter resistance is sufficiently high compared to R0, then I will be very close to a linear formula. If we take a look on resistance R0, let's say this sensor, this is a resistive position sensor, it has 5 kilo ohms, then you can calculate that with a suitable accuracy, the value of k should be larger than approximately 100. So if the voltmeter resistance is approximately 100 times larger than the sensor resistance, then with an error of about 1%, this is valid. So the result is that for this experiment, for this kind of sensor, we need a voltmeter with a relatively high input resistance. So if you use an analog voltmeter, on some ranges, it may not be suitable to use it. If you use a digital voltmeter, then it will be much better. Analog voltmeters, they typically have the input resistance of, let's say, something between 1 kilo ohm per volt to 5 kilo ohms per volt. So if you use 5 kilo ohm per volt voltmeter on, let's say, 12 volt range, then this will give you 600 kilo ohms, which is fine. But if you change the range, if you decrease it, you will have a smaller resistance. Digital voltmeters, on the other hand, they typically have a large input resistance, let's say larger than 10 mega ohms. So digital voltmeters are completely fine with this kind of sensor. When we started discussing sensors, I told you that if you are working with an analog instrument, you should always try to maximize the deflection of the needle. So you should always try to measure with when you're around the end of the scale. That's true, but here it does not apply for this kind of experiment. The reason is that if you are changing range on an analog voltmeter, you are changing the internal resistance as well. So this means that in an analog voltmeter, you are changing the value of RL over here, and this also means that you are changing the voltage that you measure. So you measure a different voltage, although the voltage is the same, and that's because of the properties of this connection. So when we will be doing the experiment here with a resistive sensor, you should not change the range on the analog voltmeter. If you are working with a digital voltmeter, it does not matter because the resistance is so large compared to the resistance of the sensor that you will not see any difference. So for this resistive sensor, you should definitely use a digital voltmeter with a high input resistance. Even the simplest digital voltmeter today has at least 10 mega ohms input resistance, so it should not cause you any trouble. In the labs, you will compare the digital voltmeter with the analog voltmeter, and you will see that there is a huge difference between the voltage that you measure for different positions. Now let's analyze a little bit further the connection for the voltage divider. We will be looking for the absolute and relative error. We know that the absolute error is the difference between the measured and the correct value. The correct value in this case will be the linear equation, and that the relative error is calculated when we compare the measured value with the correct value in percent. Let's start first with the relative error. Now, relative error is the difference between the voltage that I measure minus the correct value of the voltage. This is expressed in percent, so if I substitute the previous formulas, you can then get this result. What is important here is only the sign. The sign is always negative. So it means that the voltage that you measure is always smaller than the voltage that corresponds to the correct value. So you measure always a lower voltage. And we can see that the relative error depends on the value of K. So if I take a different voltmeter, I will have different relative error. And we see that it also depends on position. So for different positions, we'll have different relative errors. From this equation, we can also see that if I have value of K approaching infinity, when this is infinite, then this is going to 0. So if I would use a voltmeter with an infinite input resistance, I would have relative error 0. In other words, I would measure this correct voltage. From this equation, we can further calculate where is the position of maximal error. If you take this formula and calculate the partial derivative of it over x, then you can find for what position you will have the maximal error. We can do that quite easily, and you can find out that the absolute error is always the biggest in the middle. So in one half of the range, you always have the maximum error. We can calculate how large that will be. The size will depend on the value of K. We can do the same for the absolute error. So the absolute error here, you see it's the difference between the measured value and the correct value. And here you will find out that this depends on the value of K. So it depends on the value of the voltmeter resistance. Here, for this, we did find out that it does not depend on the value of K. But here it does. But roughly, for K equal 1, we can say that the maximum absolute error is somewhere about 0.7 of the range. It is changing slightly with the value of K, but not that much. So we can say that here this will be about 2/3 of the scale. Now if we plot that in a chart, we can see it directly. What you see here is a chart where you have the position from 0 to 1 here. And on the y-axis, this output voltage is normalized and related to the input voltage. So this allows me to plot this dependence for any resistive sensor. For position 0, obviously the voltage will be 0. For position 1, we will have the output voltage equal to the input voltage. The blue line here is for K going to infinity, so for an ideal voltmeter with infinite input resistance. The magenta line here is for a K equal 1. K equal 1 means it's a sensor and voltmeter with the same resistance. So for example, here in my case, I have 5 kilo ohm sensor and I would have 5 kilo ohm voltmeter. The green curve is the absolute error, and we can see that the maximum absolute error is somewhere around here. So it should be 0.69. So here we have the maximum absolute error. And the red curve is the relative error, and we see that the maximum relative error is in the middle. So regardless of what resistive sensor you take, and regardless of what voltmeter you take, it will always behave like this. So there will be always the maximum relative error in the middle. On the beginning here, around 0, you see that the relative and absolute error is 0. And the same also for the other part, the other maximum position. So here we also have the correct position. So a resistive sensor has a maximum relative error in the middle, and it measures correctly on both ends of the range. Now, what is it made from? The sensor has a resistive track, and this resistive track can be made from different materials. It can be made from a wire, then we'll call this a wire wound sensor. It can be made from an alloy of ceramics and metal, but all those materials will have different properties. The wire wound sensors are very robust. You can imagine this as a coil of wire, and you are moving the slider on this wire on the part where you have removed the insulation, and this will be very robust because it's just a wire and nothing else. Wire wound sensors, when compared to other sensors, they have typically a lower resolution. The resolution is limited by the diameter of the wire. So if you use a small diameter, then the resolution will be better. But it's a limiting factor. On the other hand, those wire wound sensors are very robust. They can work in environments where you have large vibrations, where you have changes of humidity and so forth. So they are very robust. You can use metallized layers. So it's a holder, typically of ceramics, and you have a thin layer of metallized layer on top of it. So you have higher resolution, but you are typically limited by the uniformity of the material. The resistive track typically looks like this. So let's say this is the resistive track. Here you have the fixed terminals, and this is the resistive layer itself, and then there is the slider, and the slider is moving left and right. This arrangement has quite high sensitivity to vibrations. Imagine that if I'm moving the slider all the way from the left to the right, then nothing happens typically. It's designed to work with hundreds of thousands of cycles. But what if I stay in one position, and to this position I superimpose some vibrations? So then this can damage the layer, because more cycles that this layer would last. So all this arrangement with the layers have typically this problem with vibrations. If you're moving in the whole range, then it's not a problem at all. Probably you have seen the result of this. Position sensors with metallized layers or other layers are typically used also in home appliances. So for example, if you set the volume of your amplifier, if you're listening to a CD, for example, or to a radio, then you may in time find a spot where you will not hear anything, any sound, because the layer will be damaged, and then you need to move to some other volume to hear it properly. And this is the result of exactly this damage of the layer, where you have a small hole here and you don't have the correct resistance. Metallized layers are less expensive than the wire wound sensors. They have less inductivity, but they are not as robust as the wire wound sensors. You can also use carbon. This layer does not have to be metal, but it can be carbon. That's the case of the angular sensor that I have just showed you. Carbon is very soft, so carbon resistors are not as robust as the other types. So carbon resistors are good if you want to make something really low cost, but it will not last very long time. You can use conductive plastic. That's what is used in industrial sensors. So, and that's what is used here in this resistor. Later I have some pictures. It's a layer of conductive plastic with carbon added. So it's conductive, but it does not have the bad properties of just the carbon layer. So, but it is more robust than the carbon layer itself. The last material that you see here is called cermet. Cermet is an alloy material from ceramics and metal. It can work with high temperatures. It is hard, and at the same time it allows you to do some plastic deformation. So it is one of the best materials also with the conductive plastic. So those two last materials are used in industrial sensors. You can see the data for the cermet sensors. So linearity is quite good. So linearity means how well do you fit it with a linear dependence. And you see that the difference is not that large. So it's quite a good linear sensor. I have here some examples of industrial sensors based on this principle. So this is the sensor I'm showing you here. The range depends only on the construction, so you can have small ranges, you can have large ranges. Typically, at least this sensor type can go up to 1 meter size. You can see the accuracy, it's about plus minus 1%. It has good repeatability. They say infinite resolution. Yes, it's an analog sensor. So, so the sensor is not limited in resolution by the construction, but then obviously you will be limited by the voltmeter and by its accuracy. So there is always a limit in accuracy. What is important for this sensor is that we need to connect only a certain voltage to it. So in all cases, you will find something like this. So here for another example, they say maximum voltage is 30 volts. The reason is that I need to limit current going through the sensor. So here you see 100 milliamperes is the maximal current. Here you see an example of the linear track that is inside of the sensor. This is the conductive plastic type. So here, this black part is the conductive plastic. The slider is moving on top of this, and I measure the changes of electrical resistance. Resistance sensors can be linear and angular, so they can work in both. So here you have an example of the linear sensor for linear displacement. Here you have an example of the angular displacement sensor. So you can work with both. You can use this sensor type for linear and angular displacement. You don't need any gears to transfer from linear to angular or vice versa. Any questions so far? Okay, good. So now we'll be talking about inductive sensors. Inductive sensors, they use the fact that we can measure the inductance of the coil, and in a position sensor, the inductance of the coil will be changed by the motion of our object. There are many types of inductive sensors. Today I will discuss just one, and next week I will discuss the other one. And the one I want to discuss is called LVDT. LVDT stands for Linear Variable Differential Transformer, and it's a very precise sensor for small motions, but also for large motions. So it can work with the resolution of few micrometers, but it can work also in a range of 1 meter. Of course, not with this resolution. An LVDT is this sensor. An LVDT is in fact a transformer. As you can see it from the name. And it has one movable part only. And the movable part is the core. So the core is what you see here. And the core is attached to the object. So I'm measuring the position of the object versus the core. The sensor has 3 windings. This is the primary winding, and it has 2 secondary windings. This sensor is powered by AC voltage. So here we have a power supply for AC. Typically, it's a larger frequency than the frequency in the power network. So let's say it's a few kilohertz frequency. And this AC voltage will create AC current, and here this primary coil will create AC magnetic flux. Now the magnetic flux is coupled through the core into the secondary windings, and if the windings and the core are aligned, if the core is in the middle, then I will have an induced voltage here, and here the induced voltage will be the same. So if you add them together, like I do in my connection, the sum will be 0, because you see here this winding has this polarity and this winding has this polarity, and you see they are connected in series. So when the core is aligned in the middle, the output voltage of this connection will be 0. Now if I move the core down, I will have a larger induced voltage in this winding and a smaller induced voltage in this winding. So there will be some voltage on the output. The same will happen also if I move it to the top. So I will have a larger voltage here and a smaller voltage over there. Now if we plot the dependence between position and voltage, we will see something like this. So in the central position, when x is 0, we should have the voltage 0. It's not entirely 0 because we have stray magnetic fluxes. It means we are not using all the magnetic flux in this winding. There is some leakage magnetic flux. And this magnetic flux will induce a very small voltage on the output. So this is typically a few millivolts. We'll see that also on the lab class. So this is a small voltage. It's very small, but it's non-zero. Then we have a linear section here and a linear section here. This is when the core is moving up and down, and it's not far from the other winding. The range obviously depends on construction. So this sensor has a range of about 15 centimeters. The primary winding is along the whole length of the sensor, and then you have one half of it is for one secondary winding and the other half is for the other secondary winding. So the range of the sensor is roughly one half of the size of the sensor. Now the section that you see here, here and here, the flat section, this means that the core is all the way out from the transformer and it does not have any effect on the voltage. So here I can use the sensor only in this range or in this range. Or if I combine it, I can use it from here to there. The voltage that you see here is measured with a voltmeter. But if we measure it with an oscilloscope, we'll see that also at this point something else is changing. This something else is the phase shift. So if I look on the phase shift between this voltage and between this voltage, we'll see that there will be a change. So if I combine the voltage and the phase shift together, we can see that this is the voltage, the magnitude of the voltage, and this is the phase shift. So in one quadrant you have some phase shift, and in the other one you have a different phase shift. So if you combine this together in an electronic circuit, you can have this dependence. So the output voltage is a linear function of position in the whole range. And this is exactly what is happening here in the sensor. So this sensor has an embedded electronics, so it can work with the phase shift and with the voltages, so the output is a nice linear dependence. Moreover, this sensor has a current output, so the current from 4 to 20 milliamperes correspond to position 0 to 150 millimeters. We will use this sensor in the lab, where we will measure exactly this type of dependence, and we'll also see what is the how is the current changing if we do something in the current loop. Now about deconstruction, I have already told you that there is one moving part. So this is the core, and there are 3 windings. So the primary winding is along the whole length of the sensor, and then we have 2 secondary windings. The LVDT sensor is very robust, and it's also very accurate. We'll use such sensors in the lab classes. In fact, one group has already used them. I think it was group C who was doing the force experiment. So we have used this LVDT sensor to measure the very small bending of a beam that we loaded with the force. Here you have some examples of the sensors. So they have different sizes based on the range and resolution that you require. The sensor typically looking like this is for smaller ranges, so let's say a few millimeters, but with a very high accuracy of some micrometers. The sensor that you see here, this is the slider moving in and out, so this is for larger ranges, a few centimeters, a few tens of centimeters. Typical applications. So as the sensor is very robust, you can use that in our aircraft. So it can work with changes of temperature, changes of humidity, vibrations. And one application where I found it's used is to measure the position of an aircraft thrust reverser. It's how the aircraft brakes when it lands. So the position of this mechanism is measured with an LVDT. A second application is, for example, if you roll steel or aluminium, then you need to set precisely the thickness that you want. So you have two rollers, and you need to measure very accurately the distance between the rollers. So here you see an LVDT sensor. This is movable, so you can adjust the distance between the cylinders, and you can produce the thickness of the foil that you require. The foil thickness typically is, let's say, 50 micrometers, and you need to adjust it very accurately to produce what you want. Any questions? No? Okay, good. So, the second inductive sensor will be very different. It is called a resolver. It is also an inductive sensor, but this is a sensor for angular displacement. LVDT is a sensor for linear displacement. But if you want to measure angular displacement, you have to use a resolver. A resolver is an absolute sensor. All the other sensors were also absolute. So today we will be discussing only absolute sensors, and next week we'll be discussing relative sensors. The similarity between a resolver and an LVDT is in the number of windings. A resolver uses also 3 windings. One winding is called the rotor winding and is attached to the shaft that you want to measure in an electric machine, for example. And then you have 2 stator windings. The stator windings are aligned perpendicular to each other. So here this is 90 degrees. The resolver is using the induction as well. You power the rotor winding with an AC voltage. So here you have an AC voltage. This creates an AC magnetic flux, and this magnetic flux will induce some voltage in this winding and some voltage in this winding. The amplitude of both the voltages will depend on the alignment. Here you see I have angle alpha. If angle alpha, let's define it from here to here, if angle alpha is 0, then I will have a maximum induced voltage in this winding and minimal voltage in this winding. This coil and this coil are perpendicular, so in theory there should be 0 induced voltage in this winding. In practice there will be some very small voltage due to leakage fluxes. If I change the angle alpha to 90 degrees, then the rotor winding is aligned with this stator winding. So here I will have maximum voltage, and here I will have a minimum voltage. So there will be a dependence of the voltage on the stator windings and angle alpha. We can find out that this will be a sinusoidal and a cosinusoidal dependence. So this is my rotor voltage, some amplitude times sinus omega t. The frequency of voltage that you use for a resolver is typically in a range between 2 and 10 kilohertz. You can find 15, but it's only for high-speed applications. So you power it with higher frequency, and you measure the output voltage that you have on the stator windings. So now one stator winding voltage will be also a sinusoidal function. You see here it's the same frequency times the amplitude, but times cosinus alpha. So this is this winding if I have defined alpha from here to here. So this is the cosine winding, and the other is the sine winding. So one voltage will depend on the cosine of alpha, and one will depend on the sine of alpha. Now let's fix the rotor in one position. If I fix the voltage from the generator here, from the power supply, it will be a sinusoidal voltage. I fix the rotor and I connect an oscilloscope. This is what you will see. The black curve is the reference voltage, is the rotor voltage. I power this with the power supply. The green curve, it's the sinusoidal voltage that you see over here. So I have some amplitude. The voltages are aligned, so there is no phase shift between the sinus voltage and the rotor voltage. And since this is for angle 0, so the rotor is aligned in the vertical direction, then the stator voltage marked here in yellow is 0. So we can see that here I will have 0 voltage and here I will have some amplitude. Now if I turn the rotor in a different position, let's say 90 degrees, we will have a different situation. We will have the first voltage, the sine voltage will be a sinusoidal, or this voltage is sinusoidal, and this voltage is 0. So there is definitely a dependence between the angle alpha and voltage or amplitude that I measure. Now the dependence looks like this. We'll measure it also on the lab classes. And you see that one winding will give you a sine dependence and the other winding will give you a cosine dependence. Now why do we need two windings? The reason is here in this picture. If I measure just the voltage with a voltmeter, I'm not able to distinguish what is the position. Let's say I would just look on this voltage with a voltmeter, and here if I measure this voltage, this will be the voltage, but now I have this position, but I have also this position. So I need the second winding and I need to look on the sine of the second voltage. So for example, if I select this position, then by looking on one winding, I just am able to tell, okay, I'm in this position or in this position, but without looking on the cosine winding voltage, I'm not able to tell if this is this position or if it's that position. So here at this time, I look on the sine of the voltage on the cosine winding. Here you can see it's positive, so I have this position. If it would be negative, I have this position. So for a resolver, you need to look on both voltages. Otherwise, you will just limit the range where you work. A resolver is an absolute sensor within one revolution. So you turn it on and you are able to measure directly the correct position between 0 and 360 degrees. If you want to use it in a larger range, in more revolutions, then you need to count the revolutions and it becomes a relative sensor. Now inside the resolver, we have the rotor winding. It is connected on the shaft. So here you see this is the rotor. So this is what you have in the electric motor, electric machine, and you push it on the shaft. Here we have the winding, and this is the stator that you have in the electric machine as well. So when you align those two parts together, it looks like this, and it's an absolute sensor within one revolution. Another version can look like this. So this is also a resolver, but it's an electric machine. And here you see I have a shaft. So you need a coupling and you connect it to your machine where you require to measure the position. So typically electric machines in trains or trams, they have this arrangement, and it's directly embedded in the electric motor itself. Questions? Okay, no questions. So now we'll do the Moodle test, and then in the remaining time I will make something about capacitive sensors. Okay? So the test for today is for lecture 6. The session is now started, so you can log in. In the meantime, let me repeat that next week there is no lecture because it's Easter Monday. So it's a free day, and our next lecture will be in 2 weeks. Yes, today is bonus test 5 done on 6th lecture. Okay, can I start? Okay, so I'm starting the quiz. Okay, so an LVDT is an absolute sensor. So here the answer is false. Question 2. Now you should select the equation for the output voltage. Okay, so let me just show you the schematic, and we'll discuss the result. The output voltage is a function of input voltage and R1 and R2, and it has to be this resistance, which is R2 in parallel to R1 together. So it is R2 times RL over R2 plus RL, and then it's this resistance times this resistance, plus this resistance. So now for some reason now it has shown me the text version, but did you see the equations in your questions? Okay, so it's this formula. So with the one with the R2 times R1. So this is related to last week. Semiconductor strain gauges have higher gauge factor than metallic ones. Metallic strain gauges typically have gauge factor of about 2. Semiconductor strain gauges, the gauge factor is somewhere about 120. So here the answer is true. And last one. Okay, so the highest relative error for a resistive sensor is in 1/2 of the range. The absolute error is 2/3, but the relative error is 1/2. Okay, so now let us continue in the sensors. We'll discuss a little bit capacitive sensors. Capacitive sensors are based on changes of capacity with position. And if you look on the basic formula for a capacitor, you see it here, the capacity depends on the distance between the electrodes. It depends on the area of the electrodes, and it depends on the material of the electrodes. This is expressed by relative permittivity. So we will use all three approaches for position. We can either change the distance of the electrodes, we can change the cross-section when the electrodes are looking on each other, and we can change the material. The material is related to relative permittivity. The epsilon 0 is vacuum permittivity, the value you see here. Relative permittivity is in this table. By definition, we compare all other materials to vacuum, so relative permittivity of vacuum is 1. Air relative permittivity is almost the same like for vacuum, so it's 1.000. So we can say it's also 1. The other materials have larger relative permittivity, but it's also dependent on temperature. As you see here, water for 0 centigrade has 88 relative permittivity, for 100 has 55. So there is also a quite strong dependence on temperature, which you may need to compensate if you build, let's say, a liquid level sensor based on this principle. We will first discuss the sensor that is using the changes of distance. So you can imagine we have one electrode that is fixed, we have one electrode that is moving, and by changing the distance between those electrodes, I'm changing the capacity. So it's a position sensor. The dependence of capacity and distance of the electrode is nonlinear. So it is looking like this. And the sensors designed on this principle, they are working only in a very small range. Let's say 1 millimeter roughly is the maximum range where they can move. On the other hand, those sensors will be the most accurate sensors for distance. So if you want to measure something within few nanometers, then the capacitive sensor based on this will be definitely the best one. From this equation, you can see that I'm changing the distance between the electrode and that there is a non-linear change of capacity. The other equation here, it's saying you the sensitivity, in other words, the slope at some given point. So here, if I'm doing on some point the slopes here, you see it here in this area, we have high sensitivity, and here in this area we have low sensitivity. So you should use a sensor in the area where the sensitivity is the highest. It means for a small distance. We are typically not using this sensor directly due to the non-linearity, but we are trying to combine two electrodes together and to form a differential capacitor. A differential capacitor is a device that has one electrode that is moving and two electrodes that are fixed. You see the arrangement here. The middle electrode is moving left and right, and this electrode and this electrode is fixed. So I'm changing the distance d1 between the movable electrode and the fixed electrode on the left, and then I'm changing also the distance d2. So when the electrode is moving to the left, I'm decreasing d1 and increasing d2. So capacity C1 is increasing and capacity C2 is decreasing. If you use this in a separate way, then this does not have any advantage. But if you connect this in a bridge connection, for example, you may increase your sensitivity. So this is the steady state characteristic for C1 as a function of x. This is the same for C2 as a function of x. But if you combine it together, you can have this kind of characteristic. So we see that there is a linear section almost around the origin, so around the position where the electrode is centered. And then I have a quite good sensitivity here in this area as well. So differential sensors are used, for example, in accelerometers in mobile phones, and they measure the acceleration. So not only this principle is used to get position, but it can measure acceleration, it can measure vibrations, it can measure rotational motions, and so forth. So the capacitive sensing is good for many applications. The differential capacitive sensor has roughly the same properties like the single electrode sensor. It means that it can be used in small ranges. So the distance between those electrodes is very small. Let's say maximum 1 millimeter, but typically it's something like 100 micrometers. So it's very small distance. On the other hand, it can measure very accurately. So if you want to measure within a few nanometers, then it's the best principle. The second principle is I can change the cross-section of the electrodes. So I can have one electrode that is fixed, and I can have another electrode that is moving. So I'm basically changing the cross-section between the electrodes. This is what you see here. I have one fixed electrode on the left, the other electrode, the one on the right, is moving up and down. And by this, I'm changing the cross-section between the electrodes. If we look on the equation for capacitor, this will be a linear dependence. So from a certain distance, from a certain position, I will have a linear dependence. That's fine. This change of cross-section can also be used for larger distances. So one electrode can, for example, be the tank, if it's a liquid level sensor, and the other electrode can be some buoy that is floating on this, and I can measure what is the position. So this principle is, on the other hand, good for larger distances. The principle here was good for very small distances. And the third possibility is that I can change the material. This is typically used in liquid level sensors. So you have a tank with some liquid. The tank is the electrode, and the material is what is changing the capacity directly. So we'll discuss it even further in a few classes for liquid level sensors. This has also a linear dependence. So I have some initial capacity given by the permittivity epsilon 1, and I have some other permittivity epsilon 2. Those permittivities, there should be significantly different. So I cannot measure, for example, air with this, because it has permittivity of roughly 1. But I can measure, let's say, water in a tank, because here epsilon 1 would be air with 1 permittivity, and this would be epsilon 2 water with, let's say, 80 permittivity. So there needs to be a significant difference between those two materials in terms of permittivity. Now, very often we do not have capacitors with planar electrodes, but we have cylinders. So if it is a cylinder, the capacity of the capacitor is calculated in a little bit different way. You see the formula here for a cylindrical capacitor, but it has the same structure. You see here I have epsilon, which is the material, the permittivity. I have the length, which is the length of the cylinder, and I have the ratio between the diameters. So this is a more complex formula. If, for example, in the test there is one question related to the capacity of the capacitor for this kind of application. So the answer is not this complicated formula, but it's this formula that you know from physics. Nevertheless, for the cylindrical capacitor, the dependence again is linear if we are changing cross-section. So if this is a pipe that is moving, or if it's a tank and I move the electrode up and down, it is a linear dependence. I have some examples here for capacitive sensors. The ones that you see here on the right are continuous sensors, so they give you the position information. The ones that you see here on the left side are capacitive proximity sensors that give you only yes or no, I see the object or I don't. Proximity sensors, they use a little bit different principle, but we'll discuss it next week. What can it do? Capacitive sensors are very, very accurate. So they can measure very small distances. Here, the numbers that you see here are actually from data sheets from capacitive sensors. So for example, the one that you see here has a range of 20 micrometers with a resolution of 0.2 nanometers. To give you an idea how small that is, the size of an atom is somewhere between 0.1 to 0.5 nanometers. This is hydrogen, and these are the larger atoms. So with capacitive sensing, you can measure the distance within the size of one atom, roughly. You can also measure tilt. So if you have two capacitive sensors like this, then you measure basically the distance. You can calculate the angle. Another example here, this sensor that you see on the picture has resolution of 100 micrometers and the range 100 micrometers and resolution 0.01 nanometer. You can also use capacitive sensing to get thickness of a layer. So let's say you have a metallic object and this is some paint and you want to measure the thickness. So this is one electrode, this is another electrode, and you measure the capacity. Now the condition for this is that the permittivity of the material is significantly different than the permittivity of air. So the paint here needs to have a different permittivity because otherwise I would not be able to measure it. So what do you measure here basically is again capacity. If this is thicker, I will have larger capacity than in this position, and here I will have smaller capacity. And the pictures on the right are sensors for this application. So they measure non-conductive layer thickness on conductive substrate. So this is the electrode itself, and the other electrode is the material where you have this paint layer. You can measure vibrations with capacitive sensors. So again, it's just to measure the distance. So if this is my object, if it's vibrating, I'm changing the distance. This needs to be placed on some holder that is not vibrating. I can measure relatively high frequency vibrations with that. Questions? Okay, no question. So that's it for today. Again, let me remind you that there is no lecture next week. Next week on Monday is Easter Monday, so we will meet in 2 weeks. Okay? That's all, and see you in the lab.